Oh, hi, Chris.
Hello.
Hi.
Hi, Sam.
Hi, how are you?
I'm good.
Great. Do you want to test the screen share? Do you want to test the screen share? Or it's okay?
I'm okay, I think. Yes.
Okay. All right, cool.
Hello. Hi, Chris. Hi.
Hi, Konstantinos. Hi.
Hi. Sorry for the small delay in joining. How are you?
I'm good. I'm good. Oh, well.
Good to see you. Good. Right. We should just wait for a couple of more minutes and then we can start in a bit. How are you? How are things in Chile?
No, it's well. Everything is going well. It's very busy with this project. So yes.
Great. Yes.
Yeah. But yeah, certainly I've been here 3 years in Chile, so I certainly feel very settled here now.
That's good. That's good. That's good.
No plans to go back to the UK.
To the UK, at least anytime soon.
Chile feels more stable at the moment.
Yeah. Indeed. All right. Okay, I think we can start. I will start with the introduction, and yes, we can move on. Okay. Okay, so good afternoon, everyone. Thank you for being here. So today we have the honor to have as Professor Assistant Christopher Haines, who is at the Instituto de Astronomía Ciencias Planetarias in the Universidad of Atacama in Chile. He's an assistant professor, as I mentioned, since July 2019 there. Professor Haines has been a researcher for more than 20 years with experience as a professional astronomer, received his PhD in 2001 in astrophysics from the University of Central Lancashire in the UK, and then has moved on into several postdoc positions, including Naples in Italy, the University of Birmingham, then Stewart Observatory at the University of Arizona in the US, Universidad de Chile in Santiago of Chile, Observatorio Astronomico di Brera in Milan, Italy, and since 2019 he's an assistant professor at the University of Atacama in Chile. Professor Haines' main primary area of research interest is the evolution of galaxies within groups and clusters, and understanding what physical processes, internal and external, drive the co-engine of star formation within galaxies, determining whether a galaxy evolves into being a star-forming spiral or a quiescent early type. Professor Haines is experienced in the development and carrying out of and performing the data analysis of wide field, multi-wavelength service, far UV, optical, near infrared, mid-infrared, far infrared. And it's also part of the local cluster substructure survey, the LOCUS, and also several other large spectroscopic surveys, including ACRES and VIPERS. Is currently, and this is going to be the main topic of the talk, leading the CHileAN Cluster Galaxy Evolution Survey, CHANCES, which is an ESO public spectroscopic survey that will be carried out with a new foremost multi-fiber spectrograph installed on the 4-meter VISTA telescope at Paranal in Chile. So I'll leave the stage to you. Many thanks, Chris. And
thank you very much, Konstantinos. Okay, let's see if this, I'll share the screen.
yes.
Okay.
Perfect. Thank you.
Okay, so hopefully everyone can see the screen properly. Yes, so yes, just to reiterate, my name is Christopher Haines, and I'm a professor at the University of Atacama, which is a relatively new, so this is a relatively new astronomical institute in Chile. So it's only been as a Department of Astronomy for 5 years, and I arrived there 3 years ago. So it is in a small town in the north of Chile, in the middle of the desert. So we're close to the telescopes, Las Campanas, Paranal, Cerro but in the same sort of general area of the Atacama in the north of Chile. And so, yeah, today I want to talk about the foremost instrument. So this is a new flagship spectroscopic survey facility that ESA were building to be at Paranal, and in particular the Chances survey, which I'm leading, which is a Chilean survey to study cluster galaxy evolution. And so I want to talk about foremost first, because this is a new instrument, and maybe is not it is not widely known what ESO is planning. So this is a new spectroscopic survey facility that is being developed by the foremost consortium, which will be installed next year on the 4-meter VISTA telescope at Cerro Paranal. So this is the same place as the VLT telescopes, and this will be the sole instrument on this telescope. And so this telescope will only be performing spectroscopic surveys using foremost instrument. And it's designed primarily to provide spectroscopic support for the large area surveys from the key European space missions, in particular eROSITA X-ray mission, the Gaia mission for studying stars in the galaxy, and the Euclid for studying dark energy, as well as the new ground-based facilities, including the SKA, MeerKAT, LSST, and DECAM, all in the south. And so this is particularly important because the south has not in the past has not really had sort of all-sky sort of facility for carrying out these sort of major spectroscopic surveys that have been being carried out in the north for a long time. We've had the SDSS survey going for over 20 years, providing spectroscopy for millions of galaxies across the northern hemisphere. And now we have DESI going as well, which will now provide spectroscopy for tens of millions of galaxies. And they're also installing, there's WEAVE, which is about to start in the Canary Islands. But in the south, the spectroscopic coverage has been much more intermittent and sort of reliant. They've had the 2DF and the AA Omega facilities in Australia, but ESO has never done this sort of thing. Has never had a spectroscopic survey facility before. ESO has always been sort of much more on, carrying out general purpose surveys for each individual. Everyone is, sends in proposals and carries out their own projects. But so this is a new sort of venture for ESO to have this sort of general purpose spectroscopic survey facility for supporting large scale missions. And so this is going to be installed. Also, this is the 4-meter VISTA telescope at Paranal. And so you can see the VLT telescopes in the background in the hill at the background. So it's about a couple of kilometers away from the main hill where the VLT, the 4 VLT telescopes are. And so this is but the VISTA telescope is a 4-meter telescope. And so this was built by the UK in the early 2000s and was a specialized wide field. It still is a specialized wide field survey telescope, which was built to carry out infrared imaging surveys. And it was equipped with a wide field near infrared camera called VIRCAM, which had a 1.65 degree diameter field of view, and which has been over the last 10 years or so carrying out near infrared imaging surveys, including the VISTA hemisphere survey, which obtained J and K band imaging for the entire southern hemisphere. But this is going to finish. So the VIRCAM instrument is going to be taken off the telescope at the end of the year and be decommissioned. And then next year, the telescope is going to be set up to receive the foremost instrument, and it's going to be converted into a sort of a wide field optical spectroscopic survey facility. And so this is the foremost fiber positioning system. So what it has is it has over 2,436 fibers, each of which can be sort of positioned individually, but they are all sort of allocated within a sort of a hexagonal grid over a 4.1 square degree field of view. So each of these fibers can be moved individually, but you have this they're sort of within this hexagonal grid. So you'll see this a bit clearly in a minute. So you have this, as you can see here, you see it sort of head on. You can see all of the fibers. You have the backlit here, so you can see all of the fibers installed within the foremost instrument. So where it currently is in Germany, and so you see it that it's 2.5 degrees across. And all of the fibers are individually moved on sort of to be placed on an individual star or an individual galaxy. But overall, they're constrained to be within this hexagonal grid. So we cannot move all of the fibers where we want within the field of view. They can move slightly, a few sort of, to be closer to the next adjacent fiber within the grid. But they cannot be moved significantly. So we cannot push all 2,400 fibers into the center of the field of view, as you might want to do if you want to study a galaxy cluster. But they sort of, what we end up with is this sort of overarching sort of uniform grid. So the overall density of the fibers are going to be fairly uniform across the field of view. So you end up with the coverage is going to have about 400 fibers per square degree over the field of view. But for any individual object, star or galaxy, you can place 2 or 3 fibers onto that star or galaxy. So you can see this on the right. So each of the fiber can essentially be moved sort of approximately equal to the distance to its nearest neighbors. And so it can you can always place a fiber on a given object. So there are two kinds of fibers, and so the foremost instrument will be observing simultaneously 2 different resolutions. And so there were 1,600 fibers, so-called low resolution fibers, which actually have quite a high resolution, of a resolution of 5,000. So this is about 3 times higher than that of Sloan. But it gives a complete wavelength coverage between 3,700 angstroms and going right through the optical up to 9,500 angstroms. And then you also have 800 or so high resolution fibers with a resolution of 20,000, but these are essentially just for stellar astronomy and all of the extragalactic sciences using the low resolution fibers. But the main thing to note is that essentially the fibers are sort of fixed within this. We're going to be observing uniformly across this wide field of view. So the sort of the way that the surveys are being set up and the way that the instrument has been sort of ESO has planned this is quite different from any of the other ESO surveys. And it's also quite different to the spectroscopic survey facilities. So all of the time on the 4-meter telescope is devoted to carrying out public spectroscopic surveys with foremost. And unlike all of the other ESO instruments, where all other ESO instruments, you can apply for time on any other ESO instrument, every 6 months through the normal calls, but you cannot apply for foremost time in this way. Instead, that all of the time is allocated or has already been allocated for the first 5 years. And so because it's carrying out, these are much larger long-term surveys. And so all of the surveys being carried out are over 5 years, rather than just sort of asking to time for 6 months. So 60%, 70% of the time for the first 5 years was being given to 10 public surveys from the foremost consortium. And so the foremost consortium, they were the people who developed the instrument. And so they have been given most of the time for the first 5 years to carry out the public spectroscopic surveys that they want to carry out. And the remaining 30% of time was allocated by ESO through a call of proposals, which was made in February 2020. But this includes, you have Chile always has guaranteed 10% of the time. So you ended up with that, you have the 10% was available for Chilean proposals, and 20% was available for proposals from everywhere else in the world. And 70% of the time was given to guaranteed observations from the foremost consortium. So in this call for proposals, astronomers based in Chile were very heavily advantaged, because we were, we had essentially we were getting sort of a third of the time available was for Chilean proposals. And so at the end of 2021, after a sort of very long wait, 15 so-called community surveys were approved by ESO, of which 8 have become are becoming full public surveys, so they're completely independent, and they're managing themselves, while 7 of them become sub-surveys of a consortium survey, because they're essentially they're covering the same field of view, and they're covering similar science. And so in the end, what we have are that foremost will carry out 18 public spectroscopic surveys, of which 10 are from the foremost consortium team, and 8 of them are community surveys, which were approved through the wider ESO call in 2021. And so the split is pretty even between galactic and extragalactic surveys. And all of these 18 public spectroscopic surveys will be carried out simultaneously over the first 5 years of operations of Foremost, between 2024 and 2029. And so Chances, which I'm going to talk about in a minute, is one of the 2 Chile-based surveys which were approved using the 10% of the Chilean time. And so not only is this the way that the time is allocated is quite different from other ESO surveys, also the observing strategy, how these surveys are being carried out, is actually very different to that of some of the other spectroscopic survey facilities. In particular, it's very difficult to the Weave, which is the comparator survey instrument, which is coming online in the north this year. And so in Weave, each survey uses all of the fibers in a single Weave configuration. And so, essentially you're allocating, Weave was effectively allocating a certain fraction of nights on the 4-meter William Herschel telescope in the Canary Islands. And each Weave survey essentially takes over the instrument for a certain amount of time to carry out their surveys. And so obviously their surveys are much more restricted in terms, they have to be much more fixed within the field of view of the Weave instrument. And so the surveys which can require high target densities are very much favored. But the Foremost system is very different. The way things are, the fibers are allocated and the time is allocated is very different. Instead, the fibers, the focal plane is shared by all of the surveys, such that for each individual Foremost configuration, so with all of the 2,400 fibers, these 2,400 fibers are going to be observing multiple Foremost surveys. And so, you will have at least 5 or 6 surveys with fibers centered on their targets. And each of these, and so essentially you're not the individual survey, it has very little control over the sort of the overall exposure time of the sort of individual observing block or the observing conditions. And instead, each survey is allocated a total. We all have, in the sense, all of the surveys end up having the same observing conditions, and so each survey is allocated. Instead, each survey, rather than being allocated a number of hours or nights on foremost, each survey is instead allocated total number of fiber hours. And so we allocated, fibers. And the amount of time which have been observed with each fiber over the 5-year survey. And so in a sense, each survey is uploading huge target lists, which can be everywhere over the southern hemisphere. And so it's much more suited for targeting surveys which have a low target density. You're targeting, a few objects, but over the very low density of objects, but over very wide areas of the southern hemisphere, which you can't do, if you have to take control of all of the fibers. So it's very well suited for very wide field surveys, which are covering, large fractions of the southern hemisphere. And so a lot of the surveys are essentially studying stars or galaxy populations across the entire southern hemisphere, or large fractions of the southern hemisphere. And so here you end up with a very complicated setup, where all of the 18 surveys are within having to cooperate, because we're all observing using the foremost instrument at the same time, and we're sharing. And so we end up, we're having there's a huge, essentially, we're all part of the same foremost team, the science team, in which the foremost consortium, they are responsible for organizing the overall observing strategy, so that all of the 18 main surveys are able to carry out their science successfully. And the foremost, they will, they organize, they deciding when the tiling strategy, which is maximizing the efficiency for all of the surveys simultaneously. And so we have here we show a list of the first. So these are the consortium surveys. So these were the surveys which have been carried out by the consortium team, the people who developed the foremost instrument. And so these are the ones which are given the 70% of the time. And so this is essentially a 50-50 split between galactic surveys, which are studying the Milky Way halo or the disk and the bulge, the stellar populations, and extragalactic surveys, which are, for example, ones which are aiming to provide synergies with the eROSITA surveys. So you have the eROSITA Galaxy Cluster Redshift Survey, led by Johan Comparat. And so they're trying to get measure get spectroscopic redshifts for all of the surveys which have been going, 40,000 clusters, which are going to be detected by eROSITA X-ray mission across the southern hemisphere. And then we have the active galactic nuclei survey carried out by Andrea Merlone, and so they want to get redshifts of all of the X-ray point sources which are going to be detected by the eROSITA. And then we have the WAVES wide area VISTA extragalactic survey, which is going to cover sort of 1,000 square degrees of sky, and try and get galaxies, a very high target density of galaxies across a sort of 1,000 square degrees of sky. And then we have a cosmology redshift survey, which will be measuring the large-scale structure going out to redshift 1. And we have ones looking at the time domain and the Magellanic fields. And then we have the new programs which were approved in 2021, and now sort of now having to put together the surveys this year. And so we have 8 surveys, again, with an even split between galactic surveys, looking at studying stellar populations, and extragalactic surveys, including the Chances survey, which is the one I'm leading, looking at cluster galaxy, which is focused on cluster galaxy evolution. We have another Chilean-led survey, which is S16, which is the foremost Chilean AGN galaxy evolution, called Changes, confusingly, led by Franz Bauer. And then we have another one, which is probably of wide interest for you, which is the last one, which is the 4HS survey, which is the foremost hemisphere survey of the nearby universe, led by Ed Taylor and Michel Kluver. And so, okay, I'll talk about that but so they're going to essentially, they're carrying out a survey which is going to cover the entire southern hemisphere, an extragalactic survey of the southern hemisphere. And so here I want to just highlight what the status and schedule of foremost. So we had at the end of 21, the ESO announced the final list of the 18 public spectroscopic surveys which will be carried out with foremost. And so now we are in the process, all of the surveys now are trying to put together our final list of targets. And we're through this year, and we're having to put together our photometry to select the targets across the sky. And so in the sort of early next year, all of the surveys have to provide essentially their final lists of targets to foremost. So it's not a final list, but the sort of the general structure of each survey has to be, so it will essentially be final. We'll be able to switch fibers in and out on individual objects, but we will not be able to change the overall structure of our surveys. And then in September next year, the foremost instrument will be the final acceptance of the instrument in Europe, and so they'll be confirmed that everything is working with the instrument by the end of September, and everything will be shipped out to Chile. And at the same time, we expect the VISTA telescope to be ready to receive the instrument. The mirror is going to be resilvered, and the current instrument to be taken off, and the mirror will be cleaned and improved. And then next year, early 2024, the foremost instrument we should be installed over the next 6 months afterwards. And so you have the primary acceptance of the instrument, confirmation everything is expecting to be fully functional by March 2024. And then we're starting the commissioning and the science verification phases of foremost. And we hope now that the start of Survey Ocean, all the surveys will start in September 2024, so in approximately 2 years. And so each of these 18 surveys will be carried out over 5 years. And so in principle should finish by September 2029. And the idea is then that there will be another call in 2028 or so for surveys to be carried out in the subsequent 5 years with foremost. So this just shows that essentially the aim of, so this is showing the latest. So at the moment, each of the surveys are sort of uploading sort of preliminary target lists to foremost, and the foremost is we're carrying out simulations to see how each of the surveys are working together, and the surveys can be carried out simultaneously. And so here we're showing you the current map of the target density of distribution of the targets for the low resolution instrument across the southern hemisphere for all of the 18 surveys put together. And so we can say essentially the foremost will be completely covering the southern hemisphere, going from minus 80 degrees south up to, and the plan is to generally limit the surveys to 5 degrees north. It's difficult if we extend further north, then they found that it's difficult to the efficiency of all of the surveys put together drops rather dramatically. And so we're currently limiting the survey to 5 degrees north, although that precise limit is not fixed in stone, and that with a small addition to cover the galactic plane slightly further north. And you can see that overall the coverage is reasonably uniform for the low resolution, because we want the targets being observed, particularly because we have the 4HS survey, which is going to be covering target galaxies everywhere. And some of the other extragalactic surveys are not quite covering the regions outside the galactic plane homogeneously. but rather sort of regions which are about sort of half of the southern hemisphere each. So the eROSITA, the cluster redshift survey and the cosmology redshift surveys are covering slightly different regions of the southern hemisphere, each of which is approximately half of the southern hemisphere outside. And then you have the galactic plane. You can see the target density is somewhat lower because the extragalactic surveys, which are using the low resolution fibers, are avoiding the galactic plane. And then we have some regions which are higher target densities. So we have the two sort of rectangular regions where the WAVE survey is targeting, trying to get higher target density to go out to slightly higher, so getting resolution, going out to several thousand targets per square degree, whereas the rest of the southern hemisphere, we're generally having you can see there are a few hundred galaxies or targets, or maybe 1,000 or so targets per square degree across the entire southern hemisphere. And then you have sort of high density regions in the Magellanic Clouds at the bottom, and there are a few sort of deep drilling fields. So these are the LSST drilling fields, and I think there's also the Cosmos field here in the slightly just above the equator, which will have very high target densities. But generally, we can see the foremost is designed to cover the entire southern hemisphere. And in particular, we have the 4HS Southern Foremost Hemisphere Survey, which is going to be getting spectroscopy, mostly essentially redshifts for 5.5 million galaxies across 17,000 square degrees. And the aim is to get very high completeness and in a very sort of an unbiased way, going out to sort of redshifts sort of 0.15. And so this is a sort of a simulated version of their survey based from a cosmological simulation, which is essentially showing that the area they want to coverage, and they want to go actually quite close to the galactic plane, and they're selecting objects in the near infrared using the VIRCAM VISTA data, the VIRCAM hemisphere survey, VISTA hemisphere survey to select their galaxies, enabling them to go into quite close into the galactic plane. So now the rest of the talk, I wanted to focus on the CHileAN Cluster Galaxy Evolution Survey changes. And so this is a survey which was designed particularly to be a Chilean survey. And so what we were doing at the sort of when we found out about this call for proposals from ESO, we got all of the people who are interested in cluster galaxy evolution in Chile. We all got together and started putting our heads together and what would we like to do with Foremost, and we started trying to put together a team of sort of 20 or so Chilean astronomers. So you can see the Chile flags next to all of the Chilean astronomers. And then we sort of closer to the deadline, we started getting in expertise particularly from Europe to help us put together the survey, and also colleagues in Brazil, particularly involved with the S+ survey, which is gifting high quality photometric redshifts for a large fraction of the southern hemisphere, which we want to use to help us select the targets. But so we have a management team of 7 people. So myself, Yara Hafe, Ricardo Di Marco, Alexis Funaguenoff, Paolo Maluzzi, Antonella Monachesi, and Nicolas Tejos. And sort of overall, we have sort of 40 people involved. Yeah, so mainly from Chile, Brazil, and Europe. And so what is it we're trying to do with chances? So essentially what we want to do is it's a sort of a multi-layered cluster galaxy evolution survey, but that we will be targeting approximately 300,000 galaxies, around 150 of the most massive galaxy clusters, going out to sort of redshift 0.4 to maybe going out to 0.5. And the particular aspect that we want to highlight is that we're not just targeting the visualized regions of the cluster, going out just the cores of the cluster or the visualized regions of the cluster, within R200 of the cluster, but we're particularly focusing on the infall regions, going out the surroundings of the cluster, So we can target the galaxies before they hit the cluster and see how they are transformed prior to their arrival to the cluster. And so we're going out to 5R200 for each of the clusters. So we're going a long way out of the cluster, enabling us to place each of the clusters in their cosmological context. So to map the surrounding elementary structure. And we're wanting to go down to about R of 20.5. So this is, 3 magnitudes fainter than Sloan. On all of this we're using only the low resolution spectrograph, which has an R of 5,000. So the aim, sort of fundamental aim, is to provide legacy spectroscopic support for the eROSITA X-ray mission. And so we're very much complementing the foremost, the other eROSITA cluster survey, which is the eROSITA cluster redshift survey. So what they are doing, they're just trying to get 15 or 20 redshifts per cluster, but they want to target all of the clusters that are detected by eROSITA. So they want to get, just get the primary, what is the redshift of each of the 40,000 clusters that eROSITA will detect, and get 10, 15 galaxies which are members, so that they can get the velocity dispersion of the cluster. But their focus is entirely on cosmology. But what we want to do is to study galaxy evolution within these clusters. And so what we want to do is we are targeting the rare massive clusters across the same footprint, which is essentially 10,000 square degrees outside the galactic plane. But we will be targeting essentially all of the galaxies, not just, so the other survey is going to be essentially targeting just red sequence galaxies, to maximize the efficiency, the likelihood that they are cluster members. But we need to get all of the galaxies, both star-forming and quiescent galaxies. And we want to go a long way out and to low stellar masses. But we will be doing it for 150 clusters, while they are going to try and study 40,000 galaxy clusters. So in the proposal, we were just going to match the same footprint, which we'll see in a minute, which essentially covers 10,000 square degrees, so approximately half of the southern hemisphere. But we're now, which was the eROSITA is an all-sky X-ray mission, but it's split into two. And so half of the sky is covered by there's split two. So there's the German half of the eROSITA survey, which is led by the German eROSITA team. And there's another half of the sky, which is given to the Russian half of the eROSITA team. And so only the eROSITA survey carried out by Foremost is linked to the German eROSITA team, because it's based in Munich. And so they have access to the German half of the sky. And so we were trying to match that, so they were only going to match the German half of the eROSITA footprint. But now we're trying to expand to include some of the other southern clusters, interesting massive galaxy clusters in other parts of the southern hemisphere. So we have the chances is sort of split into 3 sub-surveys. So we have the low redshift chances survey, which will be focusing on trying to survey 50 of the most massive galaxy clusters up to going up to redshift 0.07. Then we add to that, we have 2 superclusters. So these are the Shapley supercluster 0.05, and we have the Horologium supercluster 0.06. And we're also including, we want to target some of our nearest systems. Sort of these are galaxy, they're very famous galaxy clusters, sort of in the southern hemisphere, between 20 and 40 megaparsecs. So this includes the Fornax cluster and the Hydra cluster. And so for each of these clusters, we're targeting galaxies going out to 5R200, but we want to, particularly the scientific aim is that we want to go to very low stellar masses, going down to 10 to the 8, 10 to the 9 solar masses, to focus on the cluster dwarf galaxy population. So at the lowest stellar masses, the primary objective will be just to get the redshifts and place the dwarf galaxies in the cluster. But for some of the brighter galaxies in the cluster, we would be looking to get signal to noise ratio of around 20 per angstrom, allowing us to get stellar population indices the velocity dispersions of the individual galaxies, to study the galaxy populations of the star formation histories of cluster galaxies, for the sort of for the cluster galaxies maybe 10 to the 10 solar masses and above, and for the dwarf galaxies we'll probably just have the mission lines placing whether or the redshifts placing them in the cluster. And then we have the chances evolution survey, which will be targeting the 50 most massive galaxy clusters, sort of between 0.07 and going out to redshift 0.4, 0.5. We now start pushing to slightly higher redshifts, to 0.5, to track the evolution of cluster galaxies continuously over the last 4 to 5 billion years. So this is pushing these galaxy clusters will have very high target densities because they're relative. Because as the galaxy clusters are further away, the centers of the clusters are very high target densities, can reach sort of 4,000 galaxies per square degree, and so this is fundamentally is limited by the constraint of the foremost instrument, which cannot place all of the fibers in the centers of the clusters, which may only be 5 to 10 arc minutes across, whereas the field of view is 2.5 degrees across of foremost. And so, the foremost is limited to getting 400 galaxies per square degree in a single observation. And so we're going to be limited to having sort of relatively short exposures in the centers of the clusters. And so the aim is going to be simply to get the redshifts of the galaxies in these clusters. But so we'll have some difficulty of mapping these clusters in the cores of the clusters, but we'll be able to map to very high completeness the surroundings of these clusters. And so we're particularly targeting some of the clusters which have already been the centers of the clusters have been very well studied. For example, we're targeting all of the clash VLT clusters, which are very high spectroscopic completeness in the centers of the clusters. But they don't have any coverage outside the visual radius of the cluster, and so we will be mapping the surroundings of these clusters going out to 5R200, and so we'll be able to map what happens to the galaxies in the surroundings of the clusters, and merge together we will get a very high completeness overall. And we have a third sub-survey which is going to be looking at the circumgalactic medium of cluster galaxies. And so what we're planning to do is we're observing 35,000 back quasars which are behind clusters, clusters higher redshifts above redshift 0.35. And so this is particularly to search for MG2 absorption system. So MG2 is at 2,700 angstroms. And so we have to look at systems, galaxy clusters above redshift 0.35, so the MG2 absorption line, it moves into the foremost wavelength range. And so we'll be looking at quasars behind the clusters and looking for the MG2 absorption system which is absorbed by gas in the circumgalactic medium of cluster galaxies. And so we'll be observing the quasars, and we're also looking to target the 5 of the 10 nearest galaxies along the line of sight to this quasar, each of the quasars, to try and associate the MG2 absorption system to a cluster galaxy. So hopefully one of these 5 or 10 galaxies will be at exactly the same redshift as the absorption system that we detect in MG2. And so we'll be able to say this is the absorption system sampling the circumgalactic medium of this galaxy in the cluster, and to see what is the effect of the cluster on the circumgalactic medium of that galaxy. We'll be comparing that with there will be lots of absorption systems of galaxies, other galaxies, field galaxies in the same survey. And so we'll say how are the MG2 absorption system of the cluster galaxies different to those of other galaxies not in clusters, and saying what is happening to the circumgalactic medium of galaxies once they are inside the galaxy cluster. So the key science goals of chances is essentially to quantify when, where, and how star-forming spirals are being transformed, not only inside the galaxy cluster, but also around the massive galaxy clusters to build up the present day population of quiescent early type cluster galaxies as a function of stellar mass. And so particularly for the nearby galaxy clusters, we're going to go to much lower stellar masses that have been possible before. So previously, a lot of the cluster galaxy evolution surveys are focused on sort of the galaxies similar to with stellar masses above 10 to the 10 solar masses, but we're going to push down to 10 to the 9 solar masses and below. And so we'll be able to track also because we're going a long way out of the clusters, we're going to be able to track the ongoing assembly of massive clusters at late epochs. We'll be able to identify and map the surrounding filamentary structure around the clusters and map the galaxy groups in the surroundings of the galaxy cluster, which are going to be falling into the cluster, through which each of the clusters is accreting its dark matter, its mass, and also its galaxy populations. And so one of the key scientific objectives, we're going to be quantifying the importance of pre-processing in groups which are in the surroundings outside the galaxy clusters. So the galaxies are, in this case, the galaxy is transformed in the groups and then are brought into the cluster, and they've become quiescent galaxies. They've been transformed from a spiral galaxy, star-forming spiral, into a quiescent galaxy in the galaxy group, and then are later accreted into the cluster. And so how important is this process for assembling the quiescent galaxy populations that dominate the present day clusters? And so the other sort of key science objectives that we're going to probe the formation and evolution of the dwarf cluster galaxy population, for looking at galaxies with sort of masses comparable to the Magellanic Clouds. We want to track the continuous evolution of cluster galaxies over the last 4 billion years. So a lot of previous cluster galaxy evolution surveys have looked only at a very small redshift range. So they've only looked, for example, you have the WING survey, which has only looked at galaxies in the local universe, a redshift 0.05. But so you can't follow the evolution. You can say what is happening to galaxies at that redshift at 0.05. And for example, we have the LOCUS survey, which I've been involved with, which is able to say what is happening to cluster galaxies at a redshift 0.2. But you can't really, again, we're only looking at galaxy clusters in a narrow redshift range. But we could not really follow the evolution of cluster galaxies over a long period of time. So what we want to do is we will have a single survey which is going to be following galaxy clusters going out to redshift 0.4, 0.5. So this will allow us to track continuously within the same survey. We want to follow the evolution of cluster galaxies over the last 4 billion years in a consistent way. And so we also want to look at the effect of cluster environment on the gaseous content of the galaxies, and this is more at higher redshift. And so why are we interested in looking at pre-processing? So in the LOCUS survey, which I was involved with, we found that galaxies in the vicinity of clusters were more likely to be quiescent than their counterparts in typical field regions at fixed stellar mass and redshift, even a long way out from the galaxy cluster. So if we look at the figure on the left, so we have a plot of showing how the fraction of star-forming galaxies depends as a function of cluster-centric radius. So this is essentially the famous star formation density relation, although it's in terms of cluster-centric radius. And so we have the red points showing that as you go into the center of the cluster, the fraction drops down to very close to 0. But that as we go, at the radius of the cluster, we're going up to sort of 3R200. We see that even a very long way out of the cluster, this is the fraction of star-forming galaxies a long way out from the cluster. So the red points are the fraction of star-forming galaxies as defined based on Spitzer mid-infrared selection. So galaxies which have star formation rates above 2 solar masses as detected in the mid-infrared. And the pink squares show the fraction of star-forming galaxies as selected in the near ultraviolet. So they have blue, near NUV minus R colors. So they were selected as star-forming based on having near ultraviolet emission. But we found that even a long way from the cluster, 3R2 as far away as 3R200 away from the cluster. So the virial radius is R200. So even sort of 3 times the virial radius of the cluster, we found that the fraction of star-forming galaxies is sort of significantly lower than that of field galaxies at the same redshift. So here, the sort of the horizontal band here is showing what the fraction of star-forming galaxies, star formation, the fraction of galaxies which are star-forming, selected in the same way, and is coming from the same data set to be classified as star-forming for the same stellar mass and the same redshift. So the coeval galaxy populations. And so we need something to be switching off star formation before they arrive into the cluster. And even though we know that galaxies fall into the cluster and essentially bounce out the other end and can reach as far out as 2 to 2.5 virial radii from the cluster as they pass out the other end before later becoming cluster members, this cannot explain what happens. This cannot reproduce observations. So, for example, the blue solid curve shows what would happen if you had galaxies arriving into the cluster and as normal, as with hitting R200 for the first, when they hit R200 of the cluster for the first time, and are immediately quenched when they hit the cluster, and it can then still bounce out the other side of the cluster and then sort of later become virialized cluster members. You get this, you still get sort of what appears, you end up with quite you don't get, a very steep, a sharp transition at the virial radius. You get a very diagonal trend. You get a steady rising trend, even though we're switching off star formation instantaneously at R200. But you're finding that, as once we hit 3 R200, all of the galaxies are still essentially going to be will be normal field galaxies. Should appear as normal field galaxies. So we need something to be happening to galaxies, even 3 R200 away from the cluster. So to transform some fraction of the galaxies in the surroundings of the cluster prior to their arrival into the cluster. And so one way of doing this is that a certain fraction of these galaxies will be within galaxy groups, and that the surroundings of the cluster is not the same as that of the rest of the universe. And so it's still an overdense region of the universe, the surroundings of the galaxy cluster. And so you have the evolution of galaxies outside galaxy clusters is different to that for the rest of the universe. And so you can still end up having a lower fraction of star-forming galaxies, even as far out as 3 R200, or maybe even going out to 4 to 5 R200. And so this is another survey on the right. Is another observation of looking at galaxies using SDSS data including SDSS spectroscopy joint to a WISE selection in the mid-infrared to select star-forming galaxies. And again, they found that the fraction of star-forming galaxies is below that in the field, even at 3 R200. So we need something to happen to galaxies before they arrive into the cluster. And so the best way of doing this is that they're transformed in X-ray groups, galaxy groups in the surroundings of the clusters. And so previously, I looked at this for the Locus Galaxy Survey, which was a spectroscopic redshift survey, but which had a lot of X-ray data, which allowed us to look at search. So we had XMM observations for 23 galaxy clusters. We looked for XMM X-ray, extended X-ray emission of galaxy groups in the surroundings of the clusters, which we could then confirm were at the same redshift as the cluster, and so associated. They're essentially in the wider gravitational potential well of the cluster, and they're falling into the cluster, and they're going to be bringing with them galaxies which could be pre-processed. And so here on the left we have showing an X-ray map of Abell 1835, and so the XMM image was designed to study the cluster itself, and so you can see the X-ray emission from the cluster itself, but it's large enough to find extended X-ray sources at the Veal radius at R200, and maybe slightly outside. And so we were able to identify, we found if we look at all these, we have various extended sources, and then we looked for galaxies which were at the centers of these X-ray sources. So, each of these cases, many of these cases, there's, you have a bright elliptical galaxy at the center of these extended X-ray sources. And we found that we were able to identify, we had a very extensive spectroscopy of this region. And so we identified for the entire survey of 23 X-ray clusters with XMM imaging, we were able to confirm 39 infalling X-ray groups with spectroscopic redshifts, typically with 7 or more confirmed group members. And typically these are groups with velocity dispersions of around 300 kilometers per second. So these are galaxy groups with masses of a few times 10 to the 13, perhaps up to 1 times 10 to the 14 solar masses. And overall, the mass of these infalling groups is approximately 20% of the cluster mass. And we were actually able to explain half of the expected mass growth rate of clusters at late times through the accretion of these kind of galaxy groups at late times. So, but the limitation of this survey is that the XMM field of view, XMM is designed to target X-ray clusters really, but it's not designed to target very large regions of the sky. And so its limited field of view means that we could only look at galaxy groups going out to R200 or so. So we could not map the whole infall regions of the clusters. So we were able to find galaxy groups at R200, maybe going out to 1.5 R200, but not going out beyond that. So we don't know, we were not able to map the large scale structure surrounding the galaxy clusters at larger radii. But what we were able to do is we were able to confirm that pre-processing is actually happening. And so we were able to compare the fraction of star-forming galaxies in cluster members. So here we're showing the red curve. So these are the fraction of galaxies which are star-forming, but are not as a function of radius distance from the cluster. But so the red points are the galaxies which are not in the X-ray groups. And the black point triangles are showing the galaxies which are in these X-ray groups surrounding the clusters. And so in fact, the galaxies in these groups actually have the same, about the same fraction of more, or essentially as they have been pre-processed, so they're less likely to be star-forming than other galaxies at the same distance from the cluster. And indeed that they have essentially they have the same galaxy population. If we look at the galaxy populations in the groups, it's essentially the same as the population of galaxies within R200 of the clusters. And so essentially the groups are bringing in pre-processed galaxies. So the 90% of the galaxies are already quiescent in these groups. So the populations in these infalling groups are very similar to that of the cluster populations themselves. So they're bringing in already pre-processed galaxies. But we want to know now is, are they able to bring in enough galaxies to what fraction of the galaxies that we see in the clusters now are these galaxies which were pre-processed in galaxy groups rather than being transformed within the clusters themselves. And so given the limitation of the X-ray data, one of the things that we will be able to do with chance is that we'll have a synergy with the eROSITA all sky X-ray survey. So eROSITA is going to cover is an X-ray survey which is covering all of the sky, and will detect essentially all of the massive clusters in the observable universe. So this is a survey which sort of started in sort of 2019, I think. Has been paused due to the war in Ukraine, but there's still sort of 2 years worth of data, which is going to be enabling the cluster surveys to be carried out and the X-ray surveys to be carried out. And so eROSITA will detect all of the massive clusters in the observable universe, but for nearby galaxy clusters, it will not only detect the galaxy clusters, but it will also detect all of the group mass systems, the infalling groups over the entire cluster infall regions, and also the connecting filamentary structure. So this will allow us to define the environment of galaxies using their halos, the dark matter halos in which they're embedded as detected by their X-ray emission, rather than sort of the clustering of member galaxies. So this will allow you to permit you to separate the effects of intercluster medium or halo processes on galaxy evolution from essentially from galaxy density, from the interaction with other galaxies. So you're able to define the environment from the X-ray emission rather than sort of from the halo, whether a galaxy is in a X-ray halo or not. And so what we will have with eROSITA is that we will no longer have the kind of the field of view limitations that we have with XMM. And so here on the left, we have an X-ray map, which is sort of the first light eROSITA image of emerging cluster redshift 0.05, which is one of the systems that we will observe with chances. So this is the emerging cluster able 3391, 3395. And so you have the two main systems here, the two clusters here, which you would start off with. But then you can also see there are lots of other X-ray system, extended X-ray halo systems here. And so, you can imagine that quite a few of these are galaxy groups at the same redshift as these clusters, and that these are galaxy groups which are falling into, connected to the cluster and within the same sort of a filamentary large-scale structure, and that these are going to be falling into the clusters, bringing in galaxies and mass into the system. And so eROSITA is going to allow us to map the entire, large scale, place each of the clusters in the context of their large scale structure in terms of their X-ray environment. And chances will allow us to map the filaments in terms of the galaxies and place, say, what is the redshift of each of these galaxy groups? How many galaxies are there in each of these groups? What is the velocity dispersion? What is the mass of each of these galaxy groups? And allowing us to map, we will be able to map the large scale structure, connect the filamentary structure, connecting them to the main clusters. And so the aim from the proposal, the chances was going to target clusters from the German half of the eROSITA psi. And so which will be shown here in the bottom right here of the screen. And so the orange region here is showing the German half of the eROSITA sky. So this is all of the extragalactic sky sort of more than 20 degrees out of the galactic plane. So we essentially have the galactic plane, which is going through sort of band down the middle. And so you have the other parts of the southern hemisphere outside the galactic plane, but except this region here, over here on the sort of R wave around 0 and sort of declination around 0, which was part of the Russian half of the eROSITA sky, so the eROSITA for that will not be immediately available on the same timescale as the German half. The foremost cluster galaxy evolution survey, which is the consortium survey, is covering sort of 10,000 square degrees, or half of the southern hemisphere. But so we were initially going to match that survey region, but now we're going to target some galaxy clusters which are still in the southern hemisphere, but are still outside the galactic plane still, but which will not have eROSITA data immediately. There's quite a few very interesting galaxy clusters worth studying with chances. For example, Able 2744, which is one of the Hubble frontier fields, which has already been observed with the James Webb Telescope. And so these are natural surveys which will be worth observing with chances. So what we want to do with chances is essentially to place all of the clusters in their cosmological context. So you can imagine we have R200, where you have the X-ray emission, and so you have the intercluster medium, essentially, filling the region within R200. But we're going out to 5R200, and so each of the clusters, you can imagine, you have these sort of connecting filamentary structures, along which you've got galaxy groups inside these filamentary structures. And so here we've got a few galaxy groups, you can see by the purple splotches within these galaxy groups. And so you have the galaxies coming in along these filaments, and within these galaxy groups, bringing in, perhaps pre-processed galaxies into the cluster over time. And so it's important to be able to understand what happens to the cluster galaxy population, is that we're mapping the galaxies which are going to be accreted into the cluster, and follow the evolution of galaxies, looking at cluster. So if we look, for example, if we consider a galaxy cluster redshift 0.5, many of the galaxies that are outside the cluster redshift 0.5, maybe at 3R200 at redshift 0.5, will actually have fallen into the cluster by redshift 0. And indeed, half of the galaxies in present-day clusters were not in the cluster at redshift 0.5. And so it's important that we're able to map the surroundings of galaxy clusters at intermediate redshifts, because those are the galaxies, many of those are the galaxies that will be, which we have to compare directly with the galaxies which are in present-day clusters within R200. So our aim is to go out to 5R200 and to map the surroundings of the cluster. So here this is telling us what is the mass which is going to be accreted into the cluster. What are the mass in terms of galaxy groups, in terms of the filaments that are coming into the cluster. So what we want to do, so if we're comparing us to what WINGS did. WINGS was a survey from the early 2000s, which mapped 33 clusters at redshift sort of 0.05. So they were able to go to low stellar masses, but they only studied galaxies within the virial radius. And so we can then consider what we did with the locus survey of redshift 0.2. So we were able to go out to about 3R200. We were able to look at going a bit further out, look at the infall region of clusters, but we only went to sort of 10 to the 10 solar masses. So we're only looking at sort of galaxies like the Milky Way and above. So our objective is essentially to go further out than locus, and also go to comparable stellar masses as WINGS, but maybe even a bit deeper than WINGS, and go further out. For the higher redshift clusters, we're only going to actually go to similar to red stellar masses as the locus survey. So we're more or less focused on other galaxies that are 10 to the 10 solar masses. So we have one of the things we're going to be doing is we're using a sort of a near-infrared selection of targeting galaxies. So this is something that we did previously with locus, is that the near-infrared spectral energy distribution galaxies is largely independent of star formation history. So that star forming and quiescent galaxies lie along the same linear sequence in J minus K versus K magnitude diagram. So here we show on the left J minus K color of galaxies as a function of K band magnitude. And I've color-coded them according to whether they're star-forming or quiescent, which we can tell from their optical data. And so the red galaxies are the quiescent galaxies, and the blue galaxies are the star-forming galaxies. But they lie, you can see in the near-infrared, they all lie on the same sequence. But the location of the sequence actually doesn't depend, whilst it doesn't depend on their star formation history, it depends on their redshift. And so as you go to higher redshift, this entire sequence moves up, moves to redder colors. And so we can actually use the J minus K color of galaxies as a very cheap redshift proxy, at least over the redshift range between redshift 0 and redshift sort of 0.4, 0.5. And so the VISTA hemisphere survey provides very sufficiently deep J and K band photometry, certainly for the low redshift clusters. And indeed, this is the color selection that the 4HS survey are using so that they can select low redshift galaxies. They're using a J minus K color selection to select only the low redshift galaxies. And so what we do is we can select galaxies for foremost spectroscopy as those galaxies which lie on the J minus K versus K band sequence for galaxies at the cluster redshift. So this is very efficient at removing, certainly we consider we're moving background contaminants for the galaxies in the low redshift universe. So the gray points here are galaxies redshifts above 0.15. So those are the galaxies that we are not interested in if we're studying a galaxy cluster redshift 0.05. So if we did it sort of, you do a color cut just above the main, the sequence, star forming sequence, we can very quickly exclude galaxies as background galaxies in a very simple way. And so this is what we've done. We've shown that this works for the locus survey. So this is what we did previously. And so we were using this as one of the ways of doing it for selecting selecting cluster galaxies. So now I want to quickly describe what we have for all of selecting the photometry that we will have for all of our galaxies clusters. So all of the chances clusters will have have to have optical photometry, G, R, I, and Z photometry going out to about R of 23.5 from the DECAM legacy survey DR10, which is covering the entire southern hemisphere. Outside the galactic plane, sort of it goes down to about anything outside more than 20 degrees away from the galactic plane. There is now GRIZ photometry from which has been obtained from the DECAM surveys. And so the DR10, which is not public, is not the entire legacy survey is not public yet, but we have access to it as part of the foremost team to help us select. And so this is the photometry which is being used for many of the foremost extragalactic surveys. And so this is very important for the foremost because we're sharing all of the surveys are sharing we've been observing the foremost instrument at the same time. We all have to have the same astrometric system. So if we're all using the same input catalogs, the parent input catalogs from the DECAM legacy survey, we'll all be on the same astrometric system. So we won't have one survey, because we have to put the fibers efficiently onto stars and galaxies. So this is very fundamental for when we're putting we're trying to combine. We've got 18 surveys which may be using the foremost at the same time. But we also have a long-term program to obtain wide field near-infrared J, H, and K photometry, covering sort of just over a square degree field of view from VIRCAM with a 4-meter VISTA telescope for all of our target clusters between sort of redshift 0.2 and 0.5. And so we've successfully observed more than 30 of the clusters over we've had a sort of 160 hours of time observing the 30 or so clusters, which we can then add to. So there were 20 clusters observed with GCAV, which is an ESO public survey, galaxy clusters at VIRCAM, which is led by Mario Nannino, who is also in chances. So this gives us sort of the 50 galaxy clusters, which will be the evolution sample. So all of these clusters will have the deep sort of bespoke JH and K photometry, or at least J and K band photometry, allowing us to select cluster galaxies. And so these clusters are mostly selected from the Planck all-sky catalog as having masses above 7.25 times 10 to the 14 solar masses. So these are the most massive galaxy clusters in the universe at this redshift range, and they almost essentially all will have X-ray observations, existing X-ray observations from XMM or Chandra, enabling us to characterize the intercluster medium and also to detect the infalling X-ray groups already. But then they'll have eROSITA data, allowing us to get identifying X-ray groups going further out. Well, we're also working with S+ team, which is led by Claudia Mendes de Oliveira from Sao Paulo. And so they are observing 8,000 square degrees of the southern sky in 12 optical filters. And so they've built a dedicated 0.8 meter robotic telescope at Cerro Paranal in Chile, which is observing 8,000 square degrees of sky with UGR, the Sloan UGR-Z filters plus 7 narrowband filters going down to about R21. And so the objective of this survey is essentially to provide greatly improved photometric redshifts. So giving photometric redshifts which are accurate to sort of 0.016. So here is shown on the right, bottom right. And so these are the photometric redshifts for galaxies at sort of a redshift 0.05. So you're able to very efficiently select cluster galaxies using S+ data, much better than you would be able to do with just SDS photometry, or in our case we have DECAM photometry, which is GRIZ. And so this will we're going to using the S+ survey to help us select foremost targets as having a photometric redshift consistent with being cluster members. But the S+ survey only doesn't cover all of the southern hemisphere, and so we've been using CHileAN time on S+ on the same telescope to obtain S+ data over other low redshift clusters, which were not covered by the S+ main survey. So the green rectangular regions are the regions covered by the S+ main survey. And so we've been getting using CHileAN time to get observations of many of these sort of low redshift clusters outside the main S+ survey. And we have an ongoing S+ survey trying to cover the entire Shapley supercluster redshift 0.05. So the whole Logium survey redshift supercluster redshift 0.06 is actually already covered by S+ photometry, as is the Fornax cluster and the Hydra cluster. But there are other clusters which we also want to cover, which are outside the main survey. So this shows you an idea of what the photometry that we have now in hand. So we're using the CHileAN time on this 80 T80 telescope to cover the infall regions going out to 5R200 of southern 0.05 clusters. And so we have for each of these, so each of these clusters of edge 0.05, we've observed with sort of 7 S+ tiles. So each S+ tile covers 1.4 degrees by 1.4 degree. So we've been using 7 tiles. And so this essentially gives us coverage going out to approximately 5R200. So here you can see 5R200 for this cluster Abel 85. And so here we have the center. So this is the region which had been previously studied with spectroscopic coverage within R200. But what we want to do with chances is go out to 5R200. And so with S+ photometry, we have coverage over most of the region out to 5R200, but we'll have DECAM coverage, which is the blue points. We can see we have DECAM coverage everywhere essentially, and so we can cover all of the region going out to 5R200. We have definitely DECAM data, but we'll also aim to have S+ data as well for all of the S+, for all of our local clusters, nearby clusters going up to redshift 0.07. So I'm showing, so here we have we have 2 of the clusters. So I'm showing these 2 clusters because these are 2 clusters from the MeerKAT cluster galaxy legacy survey. And so here you can see what I think this is the region. So this is which is covering, I think, a 2 degree by 2 degree field of view, centered on these clusters. And so this is what we're providing radio data and maybe H1 data and radio continuum data for the regions, not just the visualized regions inside R200, but also the surroundings of the clusters. And so this should provide a very nice synergy with what we're doing with chances. So this is just gives you an idea of the footprints that we're doing for our low redshift clusters. So this is what we will have with S+. So for all of the regions, sort of the green points here, all of these galaxies, we have reliable photometric redshifts that we can use to efficiently place fibers on these targets. So yeah, so we're using these S+ photometry to identify cluster members, and then we'll use the S+ photometry to then help us get global properties of the galaxies, such as colors, stellar masses, and structure parameters and morphologies. Again, we will also have the DECAM data providing the morphologies of the galaxies, because the DECAM data will be deeper. So the chances will provide secure spectroscopic cluster membership solution, which will help the S+ surveys. And so we have a very large sort of overlap between the chances survey team and the S+ survey S+ team. And so the chances will map the large scale structure, and this will permit, feeding info galaxy groups. And so S+ is the people are very interested in pre-processing, looking at groups and filaments. And so we'll help them. And so we're also hoping that, because we're talking to you in South Africa, is that we will provide extensive spectroscopic coverage for many of the 115 clusters observed by MeerKAT as part of the MeerKAT Galaxy Cluster Legacy Survey. So we're not because you're studying most of the most massive galaxy clusters and over a similar kind of redshift range. There's actually naturally there's a lot of overlap. And And so from our side, we've interested in that sort of, you have the 1.26 gigahertz compact source catalogs from the Cluster Legacy Survey will provide a very efficient way of detecting star-forming cluster galaxies, providing unbiased estimates of their star formation rates, at least they're unbiased with respect to dust obscuration. So at the moment, we're still refining the list of galaxy clusters and some very nearby galaxy groups. So now there is sort of an opportunity to sort of coordinate targets that are being prioritized, that have already been observed by MeerKAT or will be observed by MeerKAT and MeerKAT Plus in the near future. But this opportunity, we have to do this. We would have to do this now because we have to have a definitive list of clusters. Well, indeed, we have to have it but before the end of January, even if we can adjust our target list of galaxies for on the scale of individual galaxies, but we cannot add in new galaxy clusters after January. So we have to define our clusters, which galaxy clusters and which galaxy groups we want to study now, because we can't suddenly say we want to observe target, this 1,000 galaxies for this galaxy cluster over here in this certain part of the sky, because this will then mess up. This will change the observing strategy for everybody else. So we have to define this now so that all of the surveys can be in agreement and can coordinate. But we can't do this in next year. We have to do this now. So the target selection we are doing now, but we can change targets, as we'll get more efficient, more reliable photometric redshift perhaps next year. We'll be able to perhaps refine which galaxies we're going to observe within an individual galaxy cluster. So we will still observe maybe 2,000 galaxies in an individual galaxy cluster, but we may change which 2,000 galaxies we'll be observing. But the spatial distribution will not be changing. We're about to define that next year. And so we also, we expect that it's going to be very strong synergy with the upcoming sort of H1 surveys, that will be carried out with MeerKAT and sort of and ASKAP and Wallaby surveys from South Africa, the radio arrays in South Africa and Australia, because the very large H1 gas disks are very susceptible to ground pressure stripping in galaxy clusters, and making H1 a very sensitive tracer of environmental effects. Most of the H1 detections are going to be in low mass galaxies due to their high mass galaxy functions. And so this is on the right. I think this is showing what they're expecting the H1 mass fraction of galaxies to be for the H1 detections from the Wallaby H1 survey. And so these are galaxies mostly going to be at sort of redshift 0.05 and below. And they're going to have masses sort of between 10 to the 8 to 10 to the 10 and a bit solar masses. And so, this is going to match very nicely with what we're trying to do with low redshift cluster galaxy populations. That a lot of the H1 galaxies which will be detected in H1 are going to be low masses of around 10 to the 8.5, 10 to the 9, 10 to the 9.5. So this was found for the Buddy survey, which is the thing in the middle, the panel in the middle. And so this is because these are the galaxies that we will be targeting with chances, at least for our nearby galaxy clusters. And so we will be providing the spectroscopic redshift that can then be confirmed. So the H1 service will know what the redshift of the galaxy is to look for the H1 emission for that galaxy, which will enable to put the H1 surveys to go to lower lower H1 detection thresholds. So to summarize, I want you to present foremost, but perhaps not everybody is aware of the foremost instrument that is going to be a very important. This is ESA. This is a very important instrument for ESA in Chile. So this is the flagship spectroscopic survey facility, and so this is a new venture for ESA. So this is the first time they've gone into this idea of doing something similar to SLOAN or DESI, which is going to be obtaining spectra for 25 million objects across the entire southern hemisphere over its first 5 years of operations. And and this is going to be carried out through 18 public spectroscopic surveys, starting in 2024. And so all of this data is going to be very quickly become public. And so will hopefully be of interest. Obviously, will hopefully be interest of you. You will have access to it on relatively short timescales afterwards, after a year after after observations. And Chances is going to attempt to provide highly complete spectroscopic coverage for 150 of the most massive galaxy clusters in the local universe, and out to redshift 0.5. And we're going to target approximately 300,000 galaxies. And so the main thing we're going to be doing is going a long way out, going out to 5 out to 100 to study pre-processing, and go to low stellar masses to study the formation of cluster dwarf particles population. And this will be permit very nice synergies, we hope, with the upcoming H1 surveys from South Africa and Australia. Okay, thank you very much.
Thank you very much, Chris. Well done. Thank you so much for this very thorough walkthrough, foremost, and the Chances project, and for the very detailed explanation about pre-processing groups. Very important. And also, please let me ask if any of the participants that are actually here want to ask any questions. Please raise your hands, or just write the question, or just say it out loud. In the meantime, until maybe some people are thinking of some questions, let me just ask by, let's say, a more detailed about a question about the pre-processing, about the mechanism, actually. So is it also, so for the groups that are in the surroundings of clusters, is it only what's happening in the groups that actually is that we call pre-processing, or it's also something, is a procedure that also happens as the group folds into? Is it the cluster? So which are, let's say, the most profound mechanisms of pre-processing?
Well, I think the idea of pre-processing we still don't really, it's just essentially really defined only in the sense that where it's happening. Sort of it's defined as, it's happening galaxy groups before, sort of outside galaxy clusters. So when it's the pre-processing is not defined precisely by the exact mechanism, how the galaxy is transformed in the galaxy group. So it's not saying is this one pressure stripping. It's not saying is this mergers of galaxies or interactions of the galaxies within the groups, and it could also be something that happens as the galaxy groups hits the galaxy cluster. So it's sort of been quite a loose term, I think. It's essentially, it's just to say, it's something, the transformation of galaxies in the groups before they hit the cluster. So in quite a loose sense. I think what we will hope to do with Chances is to be able to define much better what is happening to these galaxies, in a systematic way, and then hopefully, what is it, the transformation mechanism? People will be able to follow up. How are look at the galaxies in detail that are being transformed in these galaxy groups? What is happening? What is the mechanism by? What is it? Is it mergers? Is it ramp pressure stripping? So what kind of galaxy groups is this transformation happening? Are there the X-ray bright galaxy groups, or in all galaxy groups independent of the X-ray emission, above a certain mass? So this is the kind of, at the moment, is not very well defined at all. So this is the kind of thing that we would hope to do. Chances is designed really to address these kind of questions.
Great, thank you. We also have a comment and a question from a master's student from Chile, Chris, Aisharia Arun, if I'm saying that mistake correctly. Thanks for the interesting introduction to this exciting survey. I'm a master's student writing from the Universidad de Chile, and I'm interested in joining the project. Missed the initial part. So in a way, Arun is asking, what does the timeline look like in terms of joining a project as a research student? So I'm sure you can follow.
Okay, yeah. So as a research student, it's the way to join Chances is that you need to find a supervisor, a PhD supervisor who is already in Chances. And so PhD students are able to join. So the way that for joining Chances is not entirely determined by us. And so because we're part of Foremost, essentially all of the organization is done through we also have an overlying Foremost organization. And so we have to get approval from Foremost for people to join Chances now. So, I mean, everyone who was in the original proposal, Chances proposal, is automatically able to join Foremost. And so we're able to bring in a certain number of people at the postdoc level, but that's quite limited what we can do at the level of postdocs or other professors. But at the level of PhD students, we can bring in, as long as their supervisor is in Chances, any supervisor can bring in PhD students in a sort of an unlimited way. So if you want to join Chances and you are now a master's student, you need to find plenty. We have, I think, 20 or so astronomers in Chile, who are professors who have. So if you want to join Chances as a PhD student, there will be lots of PhD positions becoming available in the next years, particularly in Chile, but obviously also in Europe, but mostly in Chile. I think will be, there'll be a lot of chance for people to, also, to come to Chile and join as PhD students and also as master's students. So we can have as many master's students joining Chances and Foremost, and there's a lot of protection for their projects within the Foremost system. So this is, one of our objectives is to provide the environment for launching lots of PhD projects within Chances. And I think for my end, we wanted to make Chances, it covers a lot of different bases. So there's a lot of space for different PhD projects and master's projects, which, for example, you can study individual galaxy clusters or certain, galaxy clusters at a certain redshift. Or links, we have, if we have MeerKAT data or we have other kinds of data alongside the Chances spectroscopic data, then there'll be a lot of possibility for Chances PhD projects in the near future. Yeah.
So thanks. Yes. So it's a great time actually to start your PhD over there. Yeah. And yes, Arun says thanks for the clarification. He will speak to Sebastian Lopez from the department.
Yes.
I guess the next.
Yes.
Yeah.
Yes. So he is in the University of Chile. I think, yeah, so he is in Chances, and so he is part of the quasar, looking at the quasars behind the clusters, and so he's leading that side of the survey alongside Nicolas Tejos. But I think he is at the University of Chile. I think they are the only people. He is the only person at the University of Chile, I think, actively involved with Chances.
Perfect, great. So yeah, hopefully this can.
Yes.
Sort it out. And any other questions from the people around before we thank Chris for this, again, very detailed talk. Thank you very much. No, if not, perfect. Let's thank our speaker again. Thank you very much, Chris, for this lovely talk, and wish a good afternoon to everyone. Thank you very much.
Thank you very much for seeing us.
Thank you, Chris. Thank you. Good to see you again. Thank you so much.
Bye.
So, okay, thanks.
Okay, ciao.